If you care about what's moving through our solar system right now, you need to hear this. What astronomers just flagged isn't one object anymore, it's two, and NASA is now tracking a second fast-moving body linked to 3I Atlas. Subscribe now, because this is changing in real time. Over the past few weeks, NASA's sky surveys have been quietly updating their logs, and one line in those updates caught attention inside the Jet Propulsion Laboratory. A faint object, moving on a trajectory that looks disturbingly familiar, appeared in data pulled from wide-field surveys tied to the Atlas system, the same network that first brought 3I Atlas to the world's attention. At first, it looked like noise, a smudge, something easy to dismiss. But when analysts overlaid the motion data with earlier observations, the pattern didn't disappear. It sharpened. This new object is not random. Its speed, direction, and orbital angle place it in the same family as 3I Atlas, what researchers are now cautiously calling a sister comet. Not a fragment, not debris, but a separate body following a closely related path through interstellar space before slipping into our solar neighborhood. NASA has not used dramatic language publicly. They never do. But behind the scenes, multiple teams, including researchers connected to the Harvard-Smithsonian Center for Astrophysics, have been rechecking assumptions about how often paired interstellar objects should appear. The answer, based on existing models, is simple: almost never. Interstellar visitors are already rare. Two with linked trajectories? That's where the math starts to strain. Early tracking data comes from a mix of sources: Atlas ground-based telescopes, follow-up measurements from the European Southern Observatory, and archival sky sweeps that go back years. When those data sets are combined, the picture becomes harder to ignore. This second object entered the solar system on a path that suggests it was already traveling alongside 3I Atlas long before either became visible to us. That raises a basic but uncomfortable question. If these objects are related, where did they come from together? Natural explanations exist, and scientists are careful to lead with them. One possibility is a long-ago breakup event near another star system, ejecting two bodies on similar escape paths. Another is gravitational shepherding, where objects born far apart are later nudged into alignment by massive stars or molecular clouds. These ideas are grounded in physics, and institutions like the Vera Rubin Observatory are actively modeling such scenarios right now. But here's the problem: the timing doesn't line up cleanly. The velocities involved are unusually high. The spacing between the two objects is too consistent, and the angle at which both entered the inner solar system doesn't match what models predict for random interstellar capture. Even after accounting for observational bias, the probability curve stays stubbornly low. This is where James Webb enters the picture. While Webb was not originally pointed at the new object, its infrared instruments have been invaluable for studying 3I Atlas, particularly its thermal behavior and surface composition. Data shared between teams suggests that if the sister object has similar properties, it may soon become visible in wavelengths Webb can detect, especially as it warms slightly while approaching the Sunday. And warming matters. Comets change when they heat up. Ices sublimate. Comas form. Jets appear. But 3i Atlas already challenged expectations by showing structured activity earlier than predicted, something that forced analysts at NASA JPL to revise outgassing models on the fly. If the sister comet behaves the same way, or worse, differently, it could tell us whether these objects truly share an origin or only an orbit. There's another layer to this that hasn't gotten much public attention yet. Archived data from older observatories, including legacy Arecibo radar records and early sky surveys, are being reprocessed using modern algorithms. This is standard procedure when something unusual appears. Sometimes it leads nowhere. Sometimes it reveals that we've been missing objects like this for decades. One astronomer involved in the reanalysis put it bluntly in a closed briefing. If this is a pair, it means our census of interstellar objects is incomplete by orders of magnitude. That statement alone carries weight. Because if two linked objects slipped through until now, it suggests there may be more, not necessarily dangerous, not necessarily artificial, but unseen. And once you accept that, the solar system stops feeling as empty as we like to imagine. For now, NASA is sticking to cautious language. The sister comet is listed as a candidate interstellar object. Its orbit is still being refined. No impact risk has been identified. No official press conference has been called. But tracking has intensified. Observation windows are being scheduled, and every new data point is being compared frame by frame against what we already know about 3i Atlas. Because if these two objects are truly related, they may be carrying the same message, not in words, not in signals, but in what they reveal about how crowded, connected, and active the space between stars really is. And the next update may not be subtle at all. As more tracking data came in, something else started to stand out, and this is where things moved from interesting to unsettling. The new object wasn't just close in timing to 3i Atlas. Its trajectory, speed profile, and even how its coma behaved under solar radiation looked strangely familiar. Not identical, but close enough that researchers at NASA's Jet Propulsion Laboratory quietly began running comparative models instead of treating it as an isolated find. This wasn't announced right away. In fact, for several days the object was listed with minimal public notes, while internal teams cross-checked orbital simulations using older datasets from the Hubble spectrograph records and archived Arecibo legacy data. The reason was simple. When scientists overlaid the motion of this new comet with the reconstructed inbound path of 3i Atlas, the margins of error overlapped more than expected. In plain terms, these two objects behaved like they remembered each other. At the Harvard-Smithsonian Center for Astrophysics, astronomers reviewing infrared signatures noticed that both bodies reacted to solar heating in an unusually delayed way. Most comets begin shedding material almost immediately as they warm. These didn't. Their outer layers stayed stable longer than models predicted, then released energy in short, controlled bursts. That pattern alone doesn't prove anything exotic, but it does raise eyebrows, because it suggests internal structure that isn't uniform rubble. At the same time, the European Southern Observatory used ground-based spectroscopy to analyze gas emissions from the new comet's coma. The chemical mix was odd, not impossible, not unheard of, just rare. Certain carbon compounds appeared in ratios that usually don't survive long interstellar journeys intact. According to ESO researchers, it was as if the material had been shielded for far longer than expected. That shielding question is where things started to get complicated. Shielding implies layers. Layers imply structure. And structure forces scientists to ask whether what they're seeing formed naturally or was altered after formation. No one is claiming this object is artificial. That word isn't used in official documents. What is used are phrases like unexpected internal consistency and anomalous thermal inertia. Those phrases show up in technical briefings from NASA, JPL, and in independent reviews coming out of Keck Observatory in Hawaii. And then there's the timing. The new comet didn't just arrive near Earth's neighborhood randomly. Its approach window aligns almost perfectly with a period of heightened solar activity, the same kind of activity that affects how comets reveal their internal makeup. When the sun flares, weak structures fall apart. Strong ones don't. That's why researchers are watching closely now. Using preliminary data from the James Webb Space Telescope, analysts are trying to peer deeper into the nucleus, not just the glowing coma around it. Webb's infrared sensitivity allows scientists to estimate density variations beneath the surface. Early reads suggest the new object may have a more uniform core than most comets its size. Uniform cores are rare, natural but rare. At Stanford University, where Ronald Bracewell's old work on interstellar probes is still discussed in radio astronomy circles, a few researchers have pointed out something quietly unsettling. If multiple objects from the same distant region entered our system together, separated by time, but not origin, then what we're seeing may not be a single visitor, but debris from a larger event far outside our solar system. A breakup, a collision, or something else entirely. NASA has not confirmed a physical connection between the two objects. But they also haven't denied that the comparison is being made. And in science, silence often means the analysis isn't finished yet. Right now, both objects are being tracked daily. Every flare from the sun, every subtle shift in brightness, every unexpected emission spike is logged and reviewed. Voyager 1 telemetry data is even being referenced, not because Voyager can see the objects directly, but because its measurements of interstellar space help refine where these objects may have originated. And that's the real question hanging in the air now. Not what these objects are made of, not how fast they're moving, but where they came from and whether they arrived alone. Because if this new comet truly is a sister to 3I Atlas, then we may be witnessing the early stages of something much larger than a single discovery. Something that forces astronomers to rethink how often interstellar material enters our solar system and whether we're only now learning how to recognize it. And the next set of data expected after the object completes another solar pass may finally push this from quiet curiosity into a full scientific reckoning. What made this discovery stand out wasn't just the trajectory, but the timing. Astronomers noticed that the newly detected object entered the inner solar system along a path that looked oddly familiar. When analysts at NASA's Jet Propulsion Laboratory overlaid its orbital data with that of 3I Atlas, the resemblance wasn't subtle. The inclination, the velocity, even the way the object responded to solar radiation pressure showed parallels that are statistically rare. At first, this was treated as coincidence. Space is big, patterns repeat. That's the safe assumption. But when independent teams at the Harvard-Smithsonian Center for Astrophysics and the European Southern Observatory ran the same simulations using different data sets, the conclusions stayed the same. These two objects didn't just look alike. They behaved like siblings, not twins, not fragments from a recent breakup, but bodies that likely formed in the same environment long before our solar system existed. That idea alone changes how astronomers think about interstellar visitors. Until recently, objects like Oumuamua and 3I Atlas were considered one-offs, rare wanderers passing through by chance. But a second object, moving on a comparable hyperbolic trajectory, hints at something larger, a population, a source region, maybe even a process we haven't fully mapped yet. The Vera Rubin Observatory, even before reaching full operational capacity, provided archival sky survey data that helped trace faint pre-discovery observations. When astronomers rewound the clock, they found weak, nearly invisible streaks in old images, signatures that had been missed because no one was looking for them. Those faint streaks lined up in a way that suggested these objects didn't arrive randomly. They arrived as part of a stream. Think of it like cosmic driftwood, not one log floating alone, but pieces carried by the same current. Spectroscopic analysis deepened the mystery. Using data from the Keck Observatory in Hawaii, scientists compared the light reflected from both objects. The chemical fingerprints showed unusual ratios of carbon compounds and frozen volatiles that don't match typical solar system comets. More interestingly, both objects showed nearly identical absorption features in the infrared range, something James Webb's instruments are exceptionally good at detecting. James Webb didn't just confirm this similarity, it highlighted it. The surface temperature behavior was especially strange. As both objects approached the Sun, one would expect uneven heating, outgassing jets, and chaotic rotation. Instead, thermal readings showed smooth, controlled changes. The temperature gradients were stable, almost dampened, as if heat was being redistributed internally rather than violently escaping into space. That's not how classic dirty snowball comets act. At this point, NASA was careful with language. No dramatic press releases, no bold claims, but internally the discussion shifted. If two interstellar objects share structure, composition, and behavior, then they likely share origin. And if that origin lies outside our solar system, then whatever produced them did so in large numbers. Arecibo's legacy radar data, reanalyzed with modern machine learning techniques, offered another clue. Subtle echoes in archived recordings hinted at elongated shapes and internal density patterns inconsistent with loosely bound ice and dust. These weren't rubble piles, they were cohesive, dense. That doesn't mean artificial, it means unusual. One of the most unsettling findings came from non-gravitational acceleration measurements. Just like 3I Atlas, its newly discovered counterpart showed tiny but measurable course deviations that couldn't be fully explained by solar wind or outgassing alone. Stanford researchers familiar with Ronald Bracewell's early work on interstellar probes were quick to urge caution, reminding everyone that natural explanations must be exhausted first. Still, the numbers didn't go away. The deeper scientists looked, the harder it became to explain these objects using only models built from solar system experience. It's like trying to understand an ocean creature after only studying desert animals. the assumptions don't hold. And this is where the conversation quietly changed. Instead of asking, "What is this object?" researchers began asking, "Where do objects like this come from?" Because if two exist, more likely do. And if more exist, then our solar system isn't just being visited, it's being crossed. That realization didn't trigger panic, it triggered focus. NASA, ESA, and several university observatories began coordinating observation windows, sharing data in near real time. Voyager 1 telemetry, still whispering from beyond the heliosphere, provided baseline measurements of interstellar particle density that helped refine origin models. Hubble spectrograph records added historical context, showing that similar spectral signatures may have passed unnoticed decades ago. The picture forming wasn't of invasion or intent, but of scale. A galaxy where interstellar debris, remnants of ancient systems, and unknown formations move freely between stars, and Earth, for the first time, is paying attention. What made this moment different was not just the detection itself, but how it happened. The initial alert did not come from a single telescope, and it did not come with dramatic language. It arrived quietly through cross-correlation logs, data streams comparing orbital elements from multiple observatories at once. The same slow-moving signature was flagged independently by NASA's Jet Propulsion Laboratory in California and by analysts working with the European Southern Observatory in Chile. Two objects, similar velocity, similar inclination, similar origin vector. At first, the assumption was simple: fragmentation. Comets break apart all the time. Heat stress, tidal forces, internal pressure, these are normal processes. But as orbital reconstructions were refined using Hubble spectrograph records and follow-up observations from the Keck Observatory in Hawaii, that explanation began to wobble. The second object was not trailing debris. It was not drifting behind Three-Eye Atlas like shrapnel from a breakup. It was moving alongside it, separated by millions of kilometers, maintaining a strangely consistent spacing. That alone raised eyebrows. Then came the spectral data. Using infrared analysis from the James Webb Space Telescope, scientists compared the chemical fingerprints of both objects. Water ice, carbon monoxide, and dust signatures were expected. What wasn't expected was how closely the two matched, not just in composition, but in internal thermal behavior. Both objects exhibited temperature gradients that didn't align with standard comet models. Their surfaces cooled and warmed at rates, suggesting unusually low porosity, more like compacted material than loosely bound ice and dust. This kind of structure is rare, especially for bodies believed to have formed in the far reaches beyond the Kuiper Belt. At the Harvard-Smithsonian Center for Astrophysics, researchers began running backward orbital simulations. Where did these objects come from? Not where were they going, but where had they been? The results were unsettling. Both trajectories traced back to the same region of interstellar space. Not just the same general direction, but the same narrow corridor. A path that suggested they entered our solar system together long before either was detected. That's when the phrase sister object started circulating internally. Not twins, not fragments, sisters formed together, traveled together, entered together. but not behaving the same way. 3I Atlas continued to show subtle non-gravitational acceleration, tiny deviations that could not be fully explained by outgassing. The newly identified companion, however, remained stubbornly stable. No unexpected thrust, no measurable jets, just steady motion, like a control sample in an experiment. At Stanford University, astrophysicists revisited an old idea proposed decades earlier by radio astronomer Ronald Bracewell, the concept that advanced probes could disguise themselves as natural objects, blending into cosmic background noise. The theory was always controversial, mostly because it rested on speculation rather than evidence. But the current situation wasn't speculation, it was data. Two objects, nearly identical in composition, one behaving oddly, the other behaving perfectly. NASA did not make an announcement. There was no press conference. Instead, internal memos emphasized caution. Language like instrumental bias, model refinement, and pending verification dominated official communication. Yet behind closed doors, the tone was different. The Vera Rubin Observatory, still ramping up full operations, was tasked with wide-field monitoring. Its mission? Watch both objects continuously, not just their brightness, but their interaction with solar radiation, magnetic fields, and cosmic dust. Weeks passed. Nothing dramatic happened. And that, oddly enough, made people more uneasy. Comets usually change. They flare. They shed material. They wobble. But these two behaved with an almost disciplined restraint. Especially the second object, which showed none of the chaotic variability scientists are used to seeing. Then came the radio silence anomaly. Using legacy Arecibo data as a baseline, analysts compared background radio noise before and after both objects entered the inner solar system. The changes were subtle, so subtle they almost got dismissed, but they were consistent. A faint periodic modulation appeared in the same frequency range used by deep space telemetry. Not a message, not a signal, just a disturbance. Voyager 1 telemetry data was pulled into the comparison. Even at the edge of interstellar space, its instruments had recorded similar fluctuations, years earlier events that were never fully explained at the time. Back then, they were attributed to plasma interactions. Now, placed alongside current observations, those old anomalies took on a new weight. None of this meant life. None of it meant intelligence. And no credible scientist said otherwise. But it did mean that the solar system was no longer behaving like a closed, predictable system. Something from outside had entered, and it had not come alone. The challenge facing researchers now was no longer detection, it was interpretation. If these objects were natural, then our models of comet formation were incomplete. If they were fragments, then fragmentation mechanics were poorly understood. And if they were something else entirely, then the implications extended far beyond astronomy. NASA's language remained careful. Unusual, not unexplained. Understudy, not unknown. Still, the sheer number of institutions now involved told its own story. JPL, ESO, Keck, Harvard, Stanford, multiple space agencies sharing raw data in real time. That doesn't happen often, because collaboration at this scale usually means one thing: whatever is happening cannot be ignored. And whatever 3I Atlas brought with it, the solar system is still adjusting to its presence. The question is no longer, what are they? The question is why they arrive together and why only one of them seems to be doing something different. As more data started coming in, what caught scientists off guard wasn't just the speed of this newly identified object, but how closely its path mirrored 3I Atlas. When analysts at NASA's Jet Propulsion Laboratory ran the orbital simulations side by side, the resemblance was uncomfortable. Two bodies, different discovery dates, different sky positions, yet moving as if they remembered the same road. That alone would have raised eyebrows. What followed did more than that. Using early tracking from the Pan-STARRS network in Hawaii and confirmation from the European Southern Observatory, astronomers noticed that the so-called sister comet wasn't behaving like a typical fragment. Normally, when comets split, you see chaotic drift, uneven outgassing, and messy divergence. This object showed none of that. Its coma remained tight. Its brightness curve stayed stable. Even its rotation appeared unusually controlled for something that was supposed to be ancient ice and dust tumbling blindly through space. Researchers at the Harvard-Smithsonian Center for Astrophysics began comparing light signatures between the two objects. The reflectivity patterns, measured across visible and near-infrared bands, showed matching anomalies. Both objects reflected less sunlight than expected, yet emitted faint thermal signatures that didn't line up with known comet models. That mismatch is important. Normally, low reflectivity means cold, inert surfaces. Here, the thermal data suggested internal activity that couldn't be easily explained by solar heating alone. As this was happening, the James Webb Space Telescope quietly entered the picture. Webb wasn't tasked with hunting comets, but its infrared sensitivity made it impossible to ignore what it was seeing. Preliminary spectra hinted at complex carbon compounds mixed with unusual ratios of nitrogen and oxygen. Not proof of anything dramatic, but enough to rule out several common comet families originating from the Oort cloud. This is where the idea of a shared origin began to circulate more seriously. Not publicly, not in press releases, but inside research notes and closed-door briefings. If these objects didn't form here, then where did they come from? And more importantly, why were there two of them? Some researchers pointed back to interstellar visitor Oumuamua, the first confirmed object from outside our solar system. Avi Loeb and others had already argued that interstellar bodies don't always follow neat categories. They can look like comets without tails, asteroids without rubble, or something entirely in between. With 3I Atlas and its apparent companion, the pattern felt less random and more organized. Data from the Keck Observatory added another layer. High-resolution imaging showed subtle, repeating brightness fluctuations that lined up with rotational periods measured days earlier. That consistency matters. Natural objects tend to change as jets turn on and off. These didn't. Whatever was happening on their surfaces appeared regulated, almost restrained. At this point, NASA was careful with language. No talk of life, no talk of structures. Just careful phrasing like non-standard behavior and unusual compositional profiles. But even those phrases carry weight when they come from institutions that spend decades cataloguing boring rocks. Meanwhile, the sister comet continued to brighten faster than expected as it approached the inner solar system. its increase in luminosity didn't match the inverse square law the way classical models predicted. Instead, it followed a smoother curve, one that suggested internal processes responding gradually rather than violently. Old data was pulled back into the conversation. Arecibo's legacy radar records, long after the telescope's collapse, were re-examined for similar signatures. Buried in the noise were a handful of past detections that never made headlines, objects that passed through quietly, briefly, and were never seen again. At the time, they were written off as statistical quirks. Now they looked less random. The idea forming wasn't that these two objects were identical, but that they might be related. Like siblings shaped by the same environment, carrying the same scars, responding to the sun in similar ways. If that environment wasn't our solar system, then this wasn't just a comet story anymore. It was a traffic report. Voyager 1's plasma wave data even entered the discussion. Though far beyond the heliosphere, Voyager has been measuring subtle changes in interstellar particle density for years. Some physicists noticed weak correlations between those measurements and the estimated entry timelines of interstellar objects. Nothing definitive, but enough to suggest that the space between stars isn't as empty or as quiet as we once thought. What unsettled many researchers wasn't any single anomaly, it was the accumulation. Every explanation on its own could be rationalized. Together, they formed a pattern that resisted simple dismissal. Two objects, similar behavior, shared chemistry, controlled dynamics, and trajectories that brought them into our neighborhood not millions of years apart, but within the same astronomical blink. And hanging over all of it was a quiet question no one wanted to ask out loud just yet. If these are related, and if they didn't originate here, then how many more might be following the same path? The data keeps coming. The models keep updating. And with every new observation, the line between rare coincidence and deliberate arrival grows thinner. As more data came in, one detail began to quietly unsettle researchers. This second object, the so-called sister comet, wasn't just similar in orbit. It shared timing. When analysts at NASA's Jet Propulsion Laboratory overlaid trajectory models using updated ephemeris data, they noticed something that normally doesn't happen with random interstellar debris. Both objects entered the inner solar system on paths that were not only aligned, but staggered as if spaced deliberately rather than scattered by chance. At first, this was treated as coincidence. Space is large, after all, and strange alignments happen. But when teams cross-checked the motion using independent datasets from the European Southern Observatory and the Pan-STARRS Survey Archive, the alignment held, same inclination, similar velocity envelope, comparable non-gravitational acceleration values. That last part mattered. Non-gravitational acceleration is a polite way scientists say, this thing isn't moving the way it should. Comets usually do this when ice sublimates and vents gas like a tiny jet engine. But in both objects, the acceleration was smooth, continuous, almost regulated. Researchers at the Harvard-Smithsonian Center for Astrophysics flagged this early. They noted that typical outgassing produces erratic thrust, uneven, noisy, and dependent on solar heating. These two objects showed none of that chaos. Their velocity curves looked clean, as if shaped by a consistent internal process. NASA didn't announce this publicly, not because it was alarming, but because it wasn't explainable yet. Meanwhile, data from the James Webb Space Telescope added another layer. Webb wasn't pointed directly at either object at first. It caught them indirectly during infrared background sweeps. What stood out wasn't brightness, it was temperature. Both objects showed thermal profiles that didn't match exposed ice, rock, or dust. Parts of their surfaces remained thermally stable even as solar radiation increased. That's unusual. Most small bodies heat unevenly. These didn't. Engineers at the Space Telescope Science Institute quietly reran calibrations to rule out sensor error. They even cross-checked against Hubble's spectrograph records from older comet passes. The anomaly stayed. At this point, the working question shifted. Not, what are these objects? But why are there two? The idea of a parent-body breakup was raised. That happens. Comets fragment all the time. But fragments don't usually maintain such precise velocity matching across millions of kilometers. And they don't keep synchronized acceleration unless something is still linking their behavior. Arecibo legacy radar data archived before the telescope's collapse was re-examined for similar signatures in older interstellar visitors. Only one case came close. And even that example lacked the structural symmetry now being observed. This is where internal debate sharpened. Some teams argued the objects were rare, but natural, dense, carbon-rich bodies with unusual internal layering. Others pointed out that nature doesn't favor twins arriving on schedule. The Vera Rubin observatory simulations, still pre-operational but running predictive models, suggested a statistical likelihood so low it barely registered. Two such objects, same window, same plane, same anomalies, the odds dropped below 1 in several million. Still, no one used dramatic language. No press release, no emergency briefing, just more instruments turning quietly toward the sky. And as solar radiation increased week by week, one more detail began to emerge, something no one expected from a passive object. The distance between the two bodies was changing, not drifting, adjusting slowly, subtly, but measurably. And that's where the questions stopped being theoretical. As astronomers dug deeper into the data surrounding 3I Atlas, something else began to surface quietly in the background. It didn't come from a press release. It didn't come from a headline. It came from pattern recognition, the kind scientists at places like NASA's Jet Propulsion Laboratory and the Harvard-Smithsonian Center for Astrophysics are trained to notice even when they're not looking for it. While tracking the orbital path of 3I Atlas, researchers noticed another faint object moving along a strangely related trajectory. At first, it looked like noise, a smudge in older survey data. Something that could be dismissed as a background artifact. But when analysts cross-checked records from the European Southern Observatory and archival sky scans from Pan-STARRS and Arecibo legacy data, the same object kept reappearing, different brightness, different size, same direction. This second object wasn't following the typical scattered pattern you expect from random comets entering the inner solar system. Its motion was coherent, consistent, almost synchronized. At this point, NASA scientists stopped referring to it casually and began tagging it internally as a related body, a possible sister object to 3I Atlas. Not a fragment in the traditional sense, and not debris from a recent breakup. The spacing between the two objects was too large, and the timing too precise. Comets usually travel alone. When they don't, the explanation is violent collisions, tidal tearing near stars, or chaotic gravitational scattering. None of those explanations fit here. The sister object appeared older, fainter, and colder. Its surface reflected less sunlight, suggesting a composition rich in dark carbon compounds or highly processed ice. Observations from the Keck Observatory in Hawaii showed a spectral signature that overlapped with 3I Atlas in an uncomfortable way, not identical, but related, like two samples taken from the same environment long ago. This raised a difficult question. Where did both of these objects come from? Interstellar space is vast, but it is not uniform. Objects arriving from outside the solar system normally come from wildly different angles, with no shared history. Yet orbital backtracking models run by teams at JPL suggested that both bodies may have originated from the same stellar neighborhood millions or even billions of years ago. Not the same event, not the same breakup, the same birthplace. That idea alone forces a shift in how scientists think about interstellar visitors. It suggests that what we're seeing isn't random debris drifting in from everywhere, but a structured population bodies shaped by environments far beyond our own Sunday. As more data came in from the James Webb Space Telescope, another subtle detail added weight to this possibility. Thermal readings showed that the sister object was warming unevenly as it approached the inner solar system. One hemisphere responded faster than the other, even after accounting for rotation. That kind of thermal asymmetry is rare in natural bodies, unless something beneath the surface is influencing heat flow. No one is claiming technology, no one is claiming life. But scientists are openly acknowledging that current comet models do not explain what they're seeing. The Vera Rubin Observatory, still in its early survey phase, is expected to detect many more interstellar objects in the coming years. But 3I Atlas and its newly identified companion may already be rewriting the baseline, showing that these visitors are not isolated accidents, but members of families we've never known existed. The problem is timing. Both objects are arriving during a period of heightened solar activity. The Sun's magnetic field is more unstable than it has been in decades, and this affects observation accuracy, spacecraft safety, and communication. It also complicates predictions. Small changes in solar radiation pressure can alter the paths of low-mass bodies in ways that are hard to model precisely. NASA has been careful in its public statements, emphasizing that neither object poses a direct threat to Earth. But internally, mission planners are paying attention. Objects with uncertain mass, unusual structure, and interstellar velocity are not something you ignore, especially when more than one shows up at once. What makes this situation even more unsettling is that none of this was predicted, not by models, not by simulations, not by decades of comet studies. It's forcing astronomers to admit something uncomfortable but honest. Our understanding of what moves between stars is still incomplete. And as 3I Atlas continues its journey inward and its sister object follows on a distant, silent path behind it, one thing is becoming clear. The solar system is not as isolated as we once believed. The reason this new object matters so much is not just that it exists, but how closely its behavior mirrors 3I Atlas. When astronomers at the NASA Jet Propulsion Laboratory overlaid the orbital paths of both objects, something unusual appeared almost immediately. Their trajectories were not identical, but they were related, like branches from the same broken tree. Both objects arrived from nearly the same region of the sky. Both carried unusually high inbound velocities, and both showed signs of activity far earlier than expected for their distance from the Sunday. Normally, comets don't wake up this early. Ice stays quiet until sunlight gets strong enough to heat the surface. Yet this new comet, detected using data from the Vera Rubin Observatory's early survey simulations and confirmed by follow-up observations at the European Southern Observatory, was already developing a faint coma while still far beyond Jupiter. That alone raised eyebrows. Then came the spectroscopy. Using infrared analysis from the James Webb Space Telescope, scientists began breaking down the light reflecting off the object. This is how astronomers identify what something is made of. Water ice has a fingerprint. Carbon monoxide has one. So does carbon dioxide, methane, ammonia, and more exotic compounds. What Webb saw didn't look wrong, but it didn't look normal either. The ratios were off. The object contained water ice, yes, but mixed with unusually high levels of carbon monoxide and complex carbon compounds. That composition is closer to what scientists expect from material that formed around other stars, not from our own solar system. Researchers at the Harvard-Smithsonian Center for Astrophysics quietly began referring to it as chemically foreign, a term usually reserved for confirmed interstellar visitors like Oumuamua. That's when the comparison to 3I Atlas stopped being casual and became unavoidable. Both objects shared the same chemical oddities. Both showed early activity. Both were arriving on steep, hyperbolic-leaning trajectories that suggested they were not long-term residents of our solar neighborhood, and both appeared within a relatively short astronomical time window. This is not how comets usually behave. If this were just coincidence, it would already be rare. 2 interstellar objects in 1 decade is statistically unlikely. 2 that appear related is something else entirely. At this point, NASA began coordinating data sharing with international partners. The Keck Observatory in Hawaii was tasked with high-resolution optical imaging, while radio astronomers combed through legacy Arecibo data to see if similar signatures had been missed in the past. They found hints faint, unresolved detections from decades ago that had been dismissed as noise or catalogue errors. Suddenly, the question shifted. This was no longer about one strange comet. It was about whether 3I Atlas had company, and if it did, what that meant. One possibility is simple and unsettling. Both objects are fragments of a much larger body that broke apart long before entering our solar system. If true, then 3I Atlas is not alone, and this new comet is not a twin, it's a sibling, a remnant, a piece of something older, larger, and possibly still out there. Another possibility is even stranger. Some researchers, referencing work inspired by Stanford's Ronald Bracewell thought experiments on interstellar probes, have noted that clustered arrivals can happen when objects are gravitationally nudged together by stellar encounters. In other words, something else may have sent them here not intentionally, but as a side effect of cosmic chaos. Still, There are details that don't sit comfortably inside standard models. The new comet's rotation rate appears stable, too stable. Most small bodies tumble unpredictably, especially if they are shedding material. This one rotates smoothly, with only minor variations. That kind of balance suggests internal cohesion stronger than loose ice and dust. And then there's the timing. Both objects arrived during a period of heightened observational capability. James Webb is active. The Vera Rubin Observatory is coming online. Deep space monitoring has never been better. That raises a troubling question. Have these objects always been coming and we simply never noticed? Voyager 1 telemetry data reminds us that interstellar space is not empty. It is filled with debris, radiation, and the leftovers of star formation. If fragments like these are common, then the solar system may be passing through a stream rather than encountering a single wanderer, which leads to the problem scientists are now carefully discussing behind closed doors. If these objects are related, then their future paths matter more than their past. Orbital simulations run at JPL show that while neither object is on a direct collision course with Earth, their gravitational interactions with the giant planets could alter their paths over time. Small changes now can become big changes later. That's not speculation, it's orbital mechanics. And unlike asteroids that have been tracked for centuries, these objects are newcomers. Their behavior under solar heating is still being learned in real time. NASA is not panicking, but they are watching closely, because if 3I Atlas has a sister, then it may also have cousins. And that would mean our solar system is not just being visited, it's being passed through. What comes next depends on continued observation. Webb will keep analyzing composition. Ground-based telescopes will refine trajectories. And planetary defense teams will quietly update models, just in case. For now, there is no immediate danger. But there is a shift in perspective. For decades, interstellar objects were theoretical, rare, almost mythical. Now they're becoming familiar. And familiarity in space science often comes just before a major discovery. If you want to stay ahead of what's unfolding, not just this object, but the ones that may follow, make sure you're subscribed. The next piece of this story is already forming. And it's going to raise even bigger questions about what really moves between the stars. What's making scientists slow down right now isn't just that a second object exists, it's how closely its behavior mirrors 3I Atlas in ways that are statistically uncomfortable. When astronomers at the NASA Jet Propulsion Laboratory began plotting the orbital elements side by side, inclination, eccentricity, velocity vector, the overlap wasn't casual. It was precise enough that internal notes reportedly flagged it as non-random clustering, a phrase rarely used unless researchers are genuinely uneasy. Using preliminary data from the Pan-STARRS survey and follow-up observations from the European Southern Observatory, both objects appear to have entered the inner solar system from a similar region of interstellar space. That alone wouldn't be shocking until you factor in timing. The arrival windows are tight, the trajectories converge, and neither object behaves like a typical long-period comet disturbed by Jupiter or Saturn. One of the earliest red flags came from spectroscopy. When light from this newly identified object was split and analyzed using instruments similar to those mounted on the Keck Observatory in Hawaii, scientists expected to see the usual comet signature: water vapor, carbon monoxide, maybe carbon dioxide. Instead, the spectrum came back weak, incomplete, almost muted. This echoes what teams saw earlier with 3I Atlas. At the Harvard-Smithsonian Center for Astrophysics, researchers reviewing archival Arecibo legacy data began cross-checking whether radar echoes from the region showed any anomalies going back decades. What they found wasn't a clear detection, but a pattern of signal noise that didn't fit the background. At the time, it was dismissed as interference. Now it's being revisited. Meanwhile, the James Webb Space Telescope was quietly tasked with thermal observations, not imaging for beauty, but measuring heat. Natural objects cool in predictable ways. Ice sublimates, dust radiates. But both Atlas and its suspected sister show thermal stability that's difficult to reconcile with their size and distance from the Sunday. NASA hasn't said the word artificial. They haven't needed to. Instead, briefings have leaned heavily on phrases like unusual internal structure and energy retention inconsistent with passive bodies. When those phrases appear together in the same report, it gets attention. Even more concerning is rotation. Most comets tumble. These objects don't, at least not much. Their spin rates are slow, steady, and aligned. That alignment suggests either a shared origin event or something acting to stabilize them. According to Stanford researchers revisiting Ronald Bracewell's early ideas on interstellar probes, controlled rotation was once proposed as a way for objects to maintain orientation over long cosmic timescales. That theory was considered speculative, until now. As the data stacks up, mission planners are facing a growing problem. If these objects are fragments from the same source, natural or otherwise, then 3I Atlas isn't alone. And if one has already been detected late, others may still be inbound. This is where the concern shifts from curiosity to planning. NASA's internal risk assessments don't suggest impact scenarios. That's not the fear. The fear is uncertainty. Objects that don't behave as expected are hard to model, hard to predict, and harder to explain to the public without triggering panic or misinformation. Right now, scientists are doing what they always do when faced with something that doesn't fit: gathering more data, slowing down conclusions, and quietly expanding observation time. The Vera Rubin Observatory, once fully online, is expected to dramatically increase detection sensitivity, which could either calm nerves or confirm them. Either way, the era of treating 3I Atlas as a one-off anomaly is over, and that changes how everything that follows is interpreted. As astronomers kept tracking the so-called sister object to 3I Atlas, something subtle but important began to emerge in the data. Not dramatic at first, no explosions, no sudden turns, just small inconsistencies that refused to line up neatly with what decades of comet science had taught us to expect. The brightness curve was the first quiet red flag. When comets approach the sun, their brightness usually increases in a predictable way as ice warms and gas jets begin to form. But this object didn't follow that script. Its light output rose in steps, then flattened, then rose again, almost as if different regions were activating at different times. Researchers at the Harvard-Smithsonian Center for Astrophysics flagged the pattern as non-uniform sublimation, which is a polite way of saying the object wasn't behaving like a normal dirty snowball. Then came the spectral data. Using instruments tied to the European Southern Observatory and cross-checked with older Arecibo legacy observations, scientists examined the chemical fingerprints coming off the coma. Water vapor was present, yes, expected. Carbon monoxide, carbon dioxide, also expected. But mixed into that signal were unusually clean ratios, far more orderly than what's normally seen in natural comet outgassing. In most comets, these gases appear messy, chaotic, blended together by random fractures in the ice. Here, the ratios appeared segmented, as if different materials were venting from discrete zones. That alone doesn't mean anything artificial. Nature can be strange. But it does mean the internal structure of this object is far more organized than scientists initially assumed. As weeks passed, orbital models refined by NASA's Jet Propulsion Laboratory began to show something even more unsettling. When the trajectory of this sister object was compared side by side with 3I Atlas, their paths shared more than just origin direction. Their velocities relative to the Sun were eerily similar. Not identical, but close enough to suggest they may have experienced the same gravitational interactions long before entering our solar system. That raises a difficult question. If these objects formed together, they likely came from the same environment. But interstellar space is vast beyond imagination. The odds of two unrelated objects independently evolving such similar internal structures, compositions, and approach vectors are extremely small. That doesn't mean intention. It doesn't mean design. But it does mean shared history. And shared history implies context. At this point, several teams began quietly revisiting an old idea one most astronomers hesitate to touch publicly, the concept of interstellar fragments that are not merely debris, but remnants of larger systems. This isn't science fiction. It's been discussed seriously for decades, including by physicists like Ronald Bracewell at Stanford, who explored how advanced civilizations might leave long-lasting artifacts drifting between stars, indistinguishable at first glance from natural objects. No one is claiming that here. But when data refuses to sit comfortably inside existing models, scientists are obligated to widen the frame. Meanwhile, the Vera Rubin Observatory, still in its early operational phase, began feeding high-cadence tracking data into the global network. What it revealed was subtle but persistent. Both objects showed tiny, continuous deviations from predicted paths. Not sharp course changes, just gentle nudges, consistent over long periods. Normally, these can be explained by asymmetric outgassing jets acting like weak thrusters. But here's the issue. No corresponding jet structures were visible in high-resolution imaging from the Keck Observatory in Hawaii. In other words, the math says something is pushing. The cameras say nothing obvious is doing the pushing. This is the kind of discrepancy that keeps researchers awake at night. NASA didn't announce this as a mystery. They framed it carefully, emphasizing uncertainties, margins of error, and the limits of current resolution. But internally, according to multiple conference briefings, teams began running alternative simulations models that assumed internal mass distribution far denser and more symmetric than a typical comet nucleus. If the mass is distributed differently, then gravity alone could explain some of the anomalies. But that leads to another uncomfortable realization. A denser, more uniform interior would make these objects far older and more resilient than most known comets. Survivors of environments that shred ordinary ice bodies apart. And if they survived that long, what exactly shaped them? As Earth-based observatories handed off monitoring duties to space-based instruments, including the James Webb Space Telescope, infrared data added another layer. Webb's sensors detected thermal patterns that didn't match a loose pile of ice and dust. Heat wasn't bleeding away evenly. Some regions retained warmth longer, insulated from space in a way more typical of compact material than porous snow. Again, not proof of anything extraordinary, but also not nothing. By now, the conversation had shifted, not in headlines, but in tone. Scientists stopped asking, "What is this object made of?" and started asking, "What happened to it before we ever saw it?" Because something did. Something shaped both 3I Atlas and its newly discovered counterpart long before the sun's gravity ever touched them. And whatever that process was, it left signatures that modern instruments can't easily dismiss. As tracking continues and the objects move deeper into observational range, the next phase isn't about speculation. It's about resolution. About whether higher fidelity data will collapse these anomalies into boring explanations or sharpen them into questions we're not yet ready to answer. And that's where things begin to get very interesting. As the data streams kept coming in, one pattern refused to go away. When analysts at NASA's Jet Propulsion Laboratory overlaid the trajectory of the newly identified object with 3I Atlas, the paths didn't just look similar, they looked related. Same entry angle into the inner solar system, same unusually high velocity relative to the Sunday, same timing window, separated not by millions of years, but by what looked like a narrow cosmic gap. At that point, the working theory inside several research groups shifted. This was no longer just about a new comet. It looked like a paired arrival. Researchers at the Harvard-Smithsonian Center for Astrophysics compared spectral fingerprints from ground-based telescopes at the European Southern Observatory and the Keck Observatory in Hawaii. Both objects showed matching ratios of carbon monoxide, cyanide, and dust grain sizes that didn't line up with typical Oort cloud comets. Even more unsettling, both showed signs of non-gravitational acceleration, small but measurable changes in speed that could not be fully explained by solar heating alone. That's when the phrase sister object started appearing in internal notes. Not twins, not fragments from a recent breakup, but objects that may have formed together, traveled together through interstellar space and entered our solar system on closely timed paths. James Webb Space Telescope data pushed this further. Infrared observations hinted that the new object's coma was forming unevenly, pulsing in cycles rather than expanding smoothly. Scientists at JPL described it as episodic, as if something inside was regulating the release of material. Similar language had already been used months earlier when 3I Atlas first confused observers. At the same time, archival Arecibo legacy data was re-examined. Older, unexplained radio echoes, once dismissed as noise, suddenly lined up with the projected arrival corridor of these objects. Not signals, but reflections. as if something large and structured had passed through long before we knew where to look. NASA remained careful with its words. No claims of technology, no claims of intent. Just phrases like statistically unusual, previously unobserved class, and non-standard behavior. But behind closed doors, the concern was simpler and heavier. If two objects arrived together, how many more could be following the same path? Models run at the Vera Rubin Observatory suggested this corridor might be part of a much larger interstellar stream debris, relics, or objects captured long ago by the galaxy's gravity and only now intersecting our solar neighborhood. Voyager 1 telemetry, now far beyond the heliosphere, showed subtle variations in particle density in the same direction these objects came from. It wasn't proof, but it was enough to change how scientists were thinking. This wasn't a random visitor, and it wasn't alone. As the sister object continues its approach, and 3i Atlas drifts deeper into observation range, the question is no longer, what is it? The real question is, how many times this has already happened without us noticing, and whether we're only now developing the tools, Webb, Rubin, Keck, Voyager, to finally see it. If this discovery unsettles you, you're not alone. Stay with this channel as we continue tracking every update, every data release, and every quiet shift in what NASA is willing to say out loud. Subscribe and watch the next video on your screen, because this story isn't slowing down.